Hello and welcome back. This video will cover section 6.3, which is the second part of this set of notes for this section. So we're going to introduce, to start, some new notation for the exact area under a curve. And what we discussed in the previous video, the first part of 6.3, was in a way to approximate the area under a curve using these left or right hand sums. So this geometric method of areas of triangles. And so the left and right hand sum gave us a nice systematic way to do that, where we could control n, the number of rectangles, or equivalently the width delta x of our rectangles given a function and a fixed interval. So we're going to denote the exact area under the curve using this notation, this integrand. And so when you see this, this is telling you, this is representing the exact area under the curve of this function f, whatever that function may be, from over this interval a to b. So if you want a nice picture, just sketch any old function and we'll just make up a curve and choose an interval. So let's say a is here and b is here. So a and b are general, so they could actually, they're representing just any endpoints of any interval. But that's represented, that's one example of the geometric area that we're referring to when we write this notation. So this brings us to the definite integral, and that's the formal mathematical definition in this blue box here. And I just want to point out, so this again is just a definition for you to kind of think about, but not necessarily to memorize. This part that I've underlined here is that left-hand Riemann sum that we discussed last time. So it's a sum of these sub-areas, which are found by multiplying the height times the width. And so so that's just our left-hand sum. And then so the only new piece is the limit as n goes to infinity. So n is the number of rectangles. So we're fixing an interval and we're squeezing in more and more and more rectangles of equal width. And so when we do that, we see that that actually starts to fill in the area more and more, and we have less and less error. If we just let the limit go to infinity, then the number that approaches is the exact area under the curve. So here's a static picture of what's happening there. So if you go ahead and head to the course website and click on the practice material on the left hand side and scroll down, you can see some links, and one of them is for this applet in Desmos, and it's the definite integral compared to Riemann sums. So you can see here that you can play with the function f, the very first line on the top left, and you can also choose the number of rectangles, and you're provided with the left-hand sum calculation on the third row, and you're also provided with the exact area and some other parameters that you can play with, like a and b. So those are our endpoints of our interval, and it even gives you the delta x calculation, so the width of our rectangles. So this is just an arbitrary function, and we just chose to start 12 rectangles. So that's what our left-hand sum would look like. And so you can see that the Riemann sum comes up with, the left Riemann sum comes up with 28, about 29, and the exact area is 32, about 32. So you can actually get a better understanding of what that limit is doing. If we come back here, looking at that definition, the limit as n goes to infinity, right? So we can actually kind of see this, or think about it as a dynamic process. There's this play button. Let's see if I can scoot this over. And so you can click this play button on the left on the second row here, and if you click that, it'll start running n for larger and larger values. And you can even go so far as to customize that value. It's set to max out at 100 right now. So if we go ahead and hit play, we can get an idea of what that limit is doing as n approaches infinity. So you can see as this n is getting larger on the left-hand side, you can see what's happening. More and more rectangles are squeezing in there, and our error, some over approximation here, and so we're missing some area here. Those gaps are getting smaller and smaller and smaller, so this is becoming more and more and more refined. And as this is happening, you can notice that our Riemann sum is starting, we've started over now, so it just kind of rolls back from where it started. But coming back to the left Riemann sum here, you can see that this number is approaching the exact area. So that's what the limit is in this case 32.08. So this is a nice applet for you to play with. You can change the function, you can change all of these settings and get a deeper understanding of what this definition is telling us. So the pictures below here are a few static images of this process. So as n gets larger, you see we're squeezing more rectangles into the same interval width. And so those rectangles will of course be skinnier and they'll fill in that area a little bit better. So what they're approaching is the exact area under the curve over an interval. So thinking back to our position function s, where s is our position after some amount of time, maybe it's in hours, then we found that s prime was our velocity. And so if you were to integrate that, like we were in the last section, we were estimating the integral or the area under the curve, we found that that area represents distance. And so that means, just as an example, this integral of velocity from 0 to 6, if s prime was some velocity function, would be our net change in distance over that time period. So you can see a summary of the general definition in this boxed region here. So for right now at this stage, we'll calculate these integrals, these exact areas under curves, numerically using the calculator. So when you see this notation, you should remember that this is representing the exact area under the curve. So I'll show you how to calculate this with your calculator. So you'll enter the function into your y equals. So I'll show you two ways to do this actually. So first, go to your y equals and enter the function. So you should have something like this, and then you want to go ahead and hit that graph button and get a plot. And the important thing here is to make sure your window includes the interval that you're interested in. So 0 to 5 is our interval that we're interested in. So click your window, and this standard window goes from -10 to 10 on the x-axis based on our x-min and max, and so that looks good. So coming back here, you see in yellow on the very top row of this calculator, CALC, calc. So hit second and press that button. And number 7 here is the integral. So you can either use the keypad or just press 7. And now you see it's asking you in the corner, what do you want as your lower limit? So that will be 0. And the lower limit is always literally the lower limit on the integrand. So it's that lower number. So then you need to hit enter. And it also needs to know what's our upper limit. So it already has the function and it knows the variable. So we need to enter 5. And then what's neat about this is it actually not only calculates that area, but it shows you the shaded area. So one thing you can do is, play with the zoom if you want kind of a nicer picture, but that's really not, most of the time, that's not too important. So if you do zoom out, you see it erases your work, so then you would have to go back through and recalculate. So I wouldn't mess too much with that other than making sure that your x-min and x-max look okay. So you can see in the work below that is the answer we should get, which is 145. And so let me show you real quick another way just to do this from the home screen. So you'll go ahead and hit second quit to get back to your home screen. So once you're back at your home screen, you'll just hit math, and then you're looking for fnint for presumably function integration. So that's 9 in this calculator. And then you need to enter it in this form provided in the example. So that is to say the function, the variable, and then the lower and upper limit. And again, that order is important. So if you have a similar calculator, it should look something like this. I know the TI-84 models actually show the integrand, and they look like this form, and so it's even easier to enter in the missing values. They have little blocks where you can just enter the limits, the function, and the variable. But if you have this calculator, do make sure you close that with the parenthesis, and then you can just hit enter. And again, we see that same value of 145. So go ahead and take a minute to try these two using your calculator to make sure that you can do this quickly. So there you have it. Go ahead and if you have any issues, go back up through that example and kind of enter things there. If you have, for some reason, a different calculator like a TI-84 and you can't quite seem to figure it out, then I would definitely just do a simple Google search or YouTube search, and that's a pretty standard thing to do numerical integration. So let's look at this problem now. This is a word problem, and these are always more challenging than the procedural type problems. So the most important thing to notice here is that there's no mention of derivatives or integration or anything of the sort. So this is the point in the course where it's really important to be able to understand why the technique you think you should be using makes any sense. So we're told we have this pump delivering water into a tank, and we're given the rate as a function r of t in liters per minute, where t is time in minutes, since this pump was started, and we're asked how much water has been pumped in the first 3 minutes. So a good way to sort this out, if you're not sure what approach to take, is to think about the main tools of the course. And the main tools, most broadly, are the rate of change or derivative, and now this other tool, this new tool of integration. So you can think about what the units of the derivative would be just by dividing the units of the axes. So r of t is in liters per minute. And if we divide those axes units, then we'll get the units of the rate of change, r prime, which would be liters per minute or liters per minute squared. And of course, that's not getting us to what we want, which is how much water, right? That would be an amount in volume of liters, right? So this is not getting us where we want, and we can even, if we're really skeptical, we could just maybe take another derivative. Maybe we think some things are going to get better, but in fact they just get worse, because now it's liters per minute, or liters per minute cubed. So that tells us that those two tools of the first and second derivative aren't going to help us here. So we're pretty sure that probably it has something to do with integration, and it turns out that there's a quick way to check the units of integration. This notation is actually multiplication here between r of t, which represents the height of our function, and dt represents the width of our infinitely thin, or a rectangle's infinitely thin width. And so putting that together, we can actually write these units in liters per minute for the function. And dt is the width, so that's on the t-axis, so that's time in minutes. So in fact, the units of integration will be liters, which is exactly what we're after. So the area under this curve will represent a change in water, how much water has been pumped over a time period, provided that we choose certain fixed limits of integration. And so the first 3 minutes means we're going to integrate from 0 to 3. So the hard part of this problem is not calculating it, because our calculators will do this for us, but to know how to set this up and be confident that this is the correct approach. So let's go ahead and enter that into your calculator, and we can get the final answer. So enter that and you'll get 174, and that, as we already established, is the number of liters pumped over this time period of the first 3 minutes. So moving on to this example, we have a table, and so this asks us to find a right Riemann sum, or a right-hand sum. And so we haven't done a problem like this, so let's run through this. And for tables, in fact, we still have to use this approximate method of right-hand sums, because all we have is a series of data points for some function. We don't actually know what the function is, so the best we could do is to approximate this. So let's go ahead and draw a scatter plot of these data points. So we don't need a very detailed plot, because the only reason we're providing this plot is to give us a good idea of what we're actually trying to calculate. And so all we really need is relative heights. We don't even need to measure those ticks on the vertical axis, although you're welcome to do that if you want a better diagram. And so now we can sketch our right-hand rectangles corresponding to this interval 0 to 4 and n equals 4. So n equals 4 again means that we want 4 rectangles, and we're over this interval from 0 to 4. So each rectangle, you can see, will just have a width of 1. And if you're still uncertain about why that should be the case, you can always do the calculation. Take the width of your interval, so subtract the endpoints, 4 minus 0 in this case, and then divide by the number of rectangles, which is 4 in this case. So the ticks that we have are also the bases of our rectangles, and it's important that the diagram is really helpful here, because we see that we're not actually going to include all the data points, because we're only going over this interval from 0 to 4. So the last piece of this puzzle is to draw the right-hand rectangles, and so what that means is that for each subinterval the height of that corresponding rectangle comes from the value of the function at the right endpoint. So from 3 to 4, we're taking that function value at 4. So if you look at the table, that's this value, 4.0. So similarly, we can just move on down the line. 2 to 3, we're taking the height at the right endpoint, and so on. So there are our 4 rectangles, and now we can write out our calculation. So the right-hand sum is given by the sum of the areas of these rectangles, and so it doesn't matter if you start from left to right or right to left. So let's start on the right, just like where we started drawing. And so that means on this interval from 3 to 4, we chose the height to be this height of 4. So we have a height of 4 times a width of 1, and that's our first rectangle. And then we moved to the next subinterval, which is 2 to 3. We're taking the right endpoint to be the height, and so that was this height of 4.1 and a width of 1. And so we move on the line for each rectangle, and we have 4 rectangles in total. And so that gives us for the next one 4, a height of 4 times a width of 1, and then the last rectangle is a height of 3.8 and a width of 1. See, one thing that you see in this problem is that we don't use all of the data in the table, and that's just something that will happen depending on what the problem's asking you about. So just be aware of that, and you can always do a sanity check, because you can check that you have 4 terms and that agrees with the number of rectangles. So we get 15.9 when we add that up, and the question asks us what this tells us about petrochemical sales. This function is the sales per year in billions of tons, and T is in years. So when you multiply those, when you take the areas of each of these rectangles, you get sales, billions of sales. And so this tells us that over this time period, 0 to 4, which is 2005 to 2009, the annual petrochemical sales by this company increased by 15.9 billions of tons of sales. So the remaining problems are meant as exercises, so go ahead and take a look at those problems on your own. Hopefully you have a copy of the blank notes. Try those on your own and pause the video, and I will provide the solutions now. So there you have it. That finishes this video. Give these problems a try, and hopefully this is making sense. And as always, let your instructor know if you have any questions.